70 degrees. I felt like maybe I think that I call it the participation here. But one thing I wanted to talk about though was there's probably a lot of suspense gathering around some of these plots here. But remember what the participation or practical 2 is all about? I was giving you some interesting looking graphs to look at and to kind of get an idea about, or to look at these graphs or these plots and to think of ways that they could be somehow misunderstood, or maybe to see whether there's any kind of miscommunication that was happening inside any of these plots. And so if you go to the slide, in fact, go ahead and pull over your slides, but these other slides you should already have. These are the data analytics slides from last Tuesday. In fact, this is due today, so please get this in as soon as you can. But basically, though, you're looking at some plots. But one more thing before I get any further. There was this directory that was inside your sandbox repository, okay, the 02 practical, and inside you had a file that you were supposed to respond to, which was this file right here. What I was asking you to do was to just simply copy this whole directory into the directory or inside the repository that you get when you click on this link. Just copy the whole thing in there. So you have 02 practical. I know that the name is not the best name for this directory over here. Your repository actually is practical 1. I should have just called it practical, but I figured that actually why not just keep using that repository, because I mean it still works just fine, and it's it's there. Otherwise, I'd have to set up a new practical every time we have a practical, a new repository, and that would take some time. So go ahead and just copy everything in there, and be sure to push everything out, and then I will see it. And one more thing is, there's been some questions about why you have to do this copying yourself. Why should this file not be already found inside that repository? Well, I can answer that. The trouble is that when you have this kind of configuration for that repository, when you pull that repository, I cannot put any files in there. It's like, so for instance, like once it's been taken from, or once you've cloned it from GitHub, then the horse is out of the barn, so you can't do anything about it. And so it's just the nature of those repositories. So hopefully that's okay. But don't worry about it. Just go ahead and copy this directory into the repository that you get when you click on this link, and you're good to go. Now, let's get back to the actual things here. Maybe I can make this a bit bigger. Just give me a moment here. Let's see if page fits. Okay. So I call these like strange plots. And one of the things that we talked about was, for instance, if you look at this plot here, so you're supposed to choose 3 of these plots, and then to kind of take apart the plot itself, kind of describe what's going on, and then to investigate why it's misleading. That's in a nutshell what your instructions were for the practical. So here, this plot, I'll just go through them each and every one of them just to kind of reduce the amount of suspense that you may be going through. Look at the scale, for instance, for this global visitors to the Times website from 2004 to 2006. It goes from 0 to 10. The scale is actually not that. I mean, it's not very. There's not a huge difference between 0 and 10 when you're graphing these kinds of plots. This plot, at first glance, makes it look like something is just spiraling out of control, that everything is going straight up, and that we're actually in much worse times than we think. But when you look at the numbers, though, on the y-axis, actually, it's not so crazy. Yes, sir. There's a question. It could be in the millions. So the thing is, it's in the millions. But even then, though, it's not a huge. It's not a huge. I mean, they've look how much distance. Yeah. So the question is, the scale is in the millions, and those numbers are significant. But look how much distance there is between the on the y-axis, between the 10, the 8, the 6, the 4. It's such a. I mean, it's been kind of stretched in a way. Now maybe you're not convinced that's so shocking. I mean, maybe that's not probably, it's not the worst plot that there is, but it's making this huge thing. But the thing is, what I'm looking at though is on the other side, where, let's see, what do we have? Full price sales. The Times has that big black bar. In the histogram, it says 485,000 versus 446,000. Well, that really isn't a huge distance or difference between numbers. I mean, ultimately, if you think about the actual readerships in some of these newspapers, that isn't really a huge number. But it's showing that it's like a huge number. And so the idea is it's supposed to, it's, what do we call it? It's kind of making a contrast between the numbers. But you don't have to be convinced. I'm not saying that these are the hard and fast rules here. You don't have to be convinced. you can you can believe it or not. You can these were just chosen by some people on an analysis forum about things that are misleading. So you can believe it or not. The next one here is, again, this is what can you infer? You can see that, what do we have here? This is saying over 10 or 100 million, sorry, 100 million now receiving federal welfare. This is, again, suggesting that these numbers are spiraling out of control. And the red in these bars makes it seem a little bit more scary. So it's just kind of like you have this, you know, this is these numbers are like without stopping here. But look at where the axis for the y-axis actually begins. The y-axis actually begins at 94 million here, and so it seems like it's already up there. And then it's like kind of, and then it's talking about going to 106 million, which actually, again, it's a scaling problem here. It's not really that much when you think about 100 million people. I mean, imagine the government here and looking at these numbers here. These numbers are not very big. I hope this doesn't just blink out. I think we just lost the screen for a moment. Okay, so let's move on to the next one here. But you don't have to believe these things here. You don't have to be convinced on these. But I do want you, though, the whole point of this exercise is that I do want you to spend some time to look through plots and think to yourself, does this plot actually tell me anything? I mean, am I learning anything realistic about the data? Or am I just being misled? Am I being pushed around or something? And I don't want you to be. But okay, so this is this next plot is a little bit scary. This is saying here that common injuries that children suffer. This is saying that 5.3% of all children get spinal cord injuries. That's what it means. That's what the data could be understood to be. All children, that whole group, 5.3% of them would get spinal cord injuries. So that's really kind of scary. But surely this data isn't of all children. This must be children who have met some kind of accident or something terrible. And so what I'm saying is that if you didn't know that this was in light, or if you didn't know the context of this graph here, then you'd think that any child walking down, or if you had 100 children walking down the street, then about 6 of those children would suddenly just fall ill to a spinal cord injury. And so it's not very clearly labeled. I think that's one of the big problems is. And USA Today should have known that, should have known to make this a bit more clear. Because if you're making it, I mean, imagine another thing here. You guys, you get me all fired up. But if you, if you're making a decision based on data like this, then you only have half the story, because in this particular plot, you don't have the whole context. And so how can you really make a decision accurate? Okay, so now what are we looking at? So this is our next one here. If Bush tax cuts expire. So again, the scale is off in this graph. Okay, the scale is off. So look, it starts at about 35 and it's going up to 30 to 40. So that's just 5%? But look at it, the way that this graph is starting out, 35% is a very small drop in the bucket compared to 39.6%. And so they're making this high contrasty view between these two different plots here. And this is designed just to kind of throw you off. And so if you don't spend time actually looking at the scale, which I'll tell you, most people do not spend much time looking at the scale, which is a real shame. But they're not looking at the scale, they're not looking at the x-axis or the y-axis. They're just looking at these two bars and they're thinking, my gosh, that looks terrible. But actually this thing starts at 35 and it goes up to 39, but 35 appears to be this tiny, tiny amount, and 39.6, which is only 5%, about 5% difference, is suddenly this giant, colossal amount. So again, it's the scaling which has been, they've interfered with the scaling. Um, oh yes, this is interesting. This is interesting. Now, what can you infer in this one here? So the unemployment rate under President Obama. This was a graph was created to make Obama look unfavorable. And what I'm saying here is that look at toward the end here. So if you look at the actual right hand side of the data, you have 91, 91, 91, 98.6%, right? 8.6% is on the same plane as 9.0. So actually, unemployment in from October to November actually subsided. It went down 0.4%, which is good, but not what you see in this graph. Instead, what you see is 9.0, and then on the same, then it plateaus all the way to 8.6. Ha! Again, this is when people when people create graphs trying to mislead you. This is not drawn to scale, and so these points you kind of have to go back now and make sure these points are actually where they're supposed to be. So let's see. You can see that 9.0. You can see the difference between 9.0 and 9.1 seems to be a major hike, and the 9.2 seems to be another major hike. And then 9.2 going back to 9.1, it seems like it's dropping. And then 9.0 to 8.6 seems like there's no drop on this thing. So it's like this. It's like the points. They seem to be kind of like copied and pasted wherever the author wanted this to go. The next to this though, you have a this right down here. This arrow is talking about the real graph, the actual points where they should be if you're using a y-axis, which is actually being upheld. You can see that 8.6 is actually quite a difference between 9.0 at the far right side of the graph. Anyway, I I think some of these graphs are just shameful. Okay, now here's another one which I think is actually quite interesting. Again, it's a scaling problem. Look at this. Who agreed with the court? I believe that this is some kind of law or something that's being put together, and they're deciding whether Democrats, Republicans, or independents agreed with this law that came in, or this ruling, and they're saying that by far the Democrats agreed, for better for worse, and the Republicans did not. But 62 to 54 is actually, I mean, it's not a huge amount, but they're making this bar look like the Democrats are really out on their own here. They're really not like the other two teams here, like the other two parties. But again, it's like you have this your the scaling is being misused. Uh, okay, let's see. Mm, it's basically 6.2% versus or sorry 62 versus 54, which again isn't a huge difference. So the scale is. Okay, I'm gonna go to the next one here. So what can we infer about this? Oh yes, actually yes. This is extraordinary. Did anyone actually? Let me just ask the group here. Did anyone choose this plot? Did anyone look at this kind of or to work with? Anybody at all?
Yeah, I
So
chose this one.
you did. So can I ask you then? What did you infer? There's no right or wrong answers. I'm not gonna go.
I mean, it seems like that it was like going up, like because kind of like have the image of like um, global warming coming out of control or something. Yes,
Yes,
but some people can read it, and but it's only showing like the first half of the year. Like, I mean, of course it's going to go up because it's like
exactly, exactly, exactly. And so it's like you see this. So it's like again, it's Kobe. Thank you for that. That's genius. Thank you so much. That is exactly the issue that everyone, I think, well, that anyone, any serious data scientist would have with this, and that is that look at this. You're starting from it's saying here. What can you infer? The average monthly temperature in Fahrenheit appears to be going up. In fact, it's going up. It seems like it's going out of control. In fact, I don't see any end to this. January, February, March, April, May, June, July. Well, you know what? We've all seen these kinds of temperatures. And then they come back down again in the fall. In fact, right now, if you look outside, we're on the other side of this map. And so therefore the numbers would be going down. But here we don't see that. The only story that they're telling us is that after July, who knows what's going to happen in August? It'll keep on going up and up, and then in October it's still going up. November it's still going up. As people of habit or creatures of habit, we look at plots like this and we just imagine that the line will continue going in the direction that the plot is indicating. So Kobe, you're exactly right, 100%. Perfect. Yes. So anyway, but I do think that this is just crazy. It's like, why would they not show a whole year? Because I mean that's really the most important piece. You have to show the whole year. You have to be able to compare the hotter times with the colder times. I don't know. These plots just drive me insane. I look at these and like, oh my god, I can't believe they published this. Okay, so this is the next one. Can anyone see anything that's absolutely insane about this one here? Did anyone choose this one? It's actually a little bit more, I guess, complicated here. But um, the problem with this is they would call this an incomplete plot, and by that, what they're saying is that you don't have the full story, you don't have the full, there's no full context, and so you're looking uh, at these numbers here, and they just look like they were already high, and then and you don't see them kind of like you don't see them kind of dropping off. So it says here that this graph, I mean, basically, it makes it look like the deficit has already been high. I mean, the graph starts in 2009, which is already high, and it might make you believe that this high graph from 2009 is kind of an ongoing problem here. But um, the definite, I mean, looking at this plot here, the deficit was in 2007, I think. Actually, it wasn't as high as this. In fact, you wouldn't know this, but it's an incomplete graph though, because there's actually before 2009, the numbers were actually much lower. 2009, there's a bunch of spending going on, and so you see this deficit going up, but you don't see anything about how the deficit got there. And so this is again kind of it's not telling you the full story, and the full story is that the deficit was not always that high. It was actually much lower, and you'd only know that if you were an economist or someone in political science who'd spent some time actually studying these things. But otherwise, you wouldn't know. In fact, I didn't know. I had no idea. But sorry, I mean, I looked it up, and you see in 2007, it was I guess it was like it was much it wasn't as high as 1.5. It was like 1.1 or 1.2 or something, but it wasn't that high. And so anyway, but it's there. So this is an incomplete plot, and so when you're putting out information like this, you're trying to deceive the public, and you don't show them the whole story. You just show them the pieces of the story, which make it seem like the deficit was already really high. Now, this plot, did anyone choose this plot, by the way? Choose it? This one was tricky. Um, it takes a long time, actually, to kind of get this notion. But then this is like some kind of internet meme here. Like, once you see it, it's like, ah. And once you see it, the thing is, though, that this has two different y-axes. That is a great faux pas. That means you cannot do that. You cannot have two different y-axes. I don't know whether, so I have on my screen here, I see kind of a dark blue and a gray line. Maybe it's a black line. It looks dark blue on my screen here. Now, uninsured Americans unemployment rate. I don't know really which, I mean, I have these numbers, or I have like, labels on my y-axis here, but I'm not really sure why it is that I can compare those two sets of numbers. It's not clear to me that uninsured Americans' unemployment rate are actually comparable. And who's to say that the scales that they chose for uninsured Americans and unemployment rate is actually comparable? That's like me making a plot saying people who loved Star Wars and people who loved I don't know, Lord of the Rings. Two different giant movie franchises here. Really different stories, different time settings, different types of themes. I can't compare necessarily those two movies together. I can say that these are both different fans of these movies, but maybe I'm not allowed analytically here to say that I can't compare one group with the other. It's apples and oranges. And here they're comparing uninsured Americans, unemployment rate, and they're both saying that somehow they are both jumping up and they converge in November 2008. Is that true? is that really, I mean, is there any truth in that convergence? And what does a convergence mean? And so what I'm trying to say, though, is that this graph is just completely fabricated. It's maybe the data was true before it was superimposed together. Maybe there was some truth in it. But as it stands right now, though, they're inferring that there's a correlation between two different types of data, and they haven't suggested why that correlation exists. One thing that we're going to be actually talking about today, is correlations. We're going to be talking about why is it that we can actually say that something is similar to something else. If I say that the more time you spend studying, the better your grades are, that's a correlation. That means the more you do on this side, the more you see on this side. And so that's a correlation. But over here, though, this is suggesting a correlation exists, but really there isn't. Um, anyway, this is all, it's all speculative. So please do go ahead, push up your practical. Do not forget, just push up whatever you have. It's a check mark grade, and I will find it. I'm going to go now to another thing here. I hope you had fun, by the way. You had fun with these plots. They're not designed to give you headaches. They're designed to show you, for instance, by the way, that you have to be smarter than your average bear when you're looking at some of these plots here, because you'll find that some people are trying to feed you all kinds of junk. You have to be smarter. You have to look at these things. Look at the x-axis. Look at the y-axis. Look at the scale. Does it make sense? Are these pieces being correlated unnecessarily? Or is there something going on? So anyway, you have to kind of keep watching that. One thing I want to talk about, though, don't forget that I'm putting up the channels on YouTube for our class. Go ahead and click on this link down here for class videos, and you'll find all the videos from our course. I'm going to show you this planning your time, and that is that we have, sorry, now we are October 22nd. Goodness gracious. So that puts us about right here. I think that's right. Yeah, that puts us right here. So this week, what we're doing is I've changed this planning your time. We're doing basic stats and linear models. This will take us until week 9. Next week, we have a speaker coming to talk to us, Dr. Eckstein, who's going to be talking about doing work in psychology using data analysis. Fantastic talk. I mean, it really is. It is really quite exciting to see that the analysis that all these disciplines do is actually not so different from the analysis that any other discipline. We're all somehow unified by the nature of our interest in working with data. But we do have an exam coming up, though, on the week of the 10th here. That's the first week of November. And so I'm thinking that on the week of the 9th here, I will give you some kind of an idea about what to expect. But the exam 2 is probably going to be very, very similar to the exam that we had for exam 1 in this class, where you'll have some work that you have to, you'll be take home, obviously. You'll have some work that you can do on R, and then you have to respond to some questions. But anyway, more on that later. That's just so that you have an idea about what to expect. It should be now in your forecast of things that are going to happen in this class, and so it should be. I think that's it. I'm just looking through my notes to see whether there's anything else I need to tell you before we actually get started with the notes here. Please go ahead and get started with your or pulling over your repository. You'll find the new slides in there. I'm going to cover today, and these new slides are here. There we go. And so we have week 8, or the 22nd of October, fall. Now, one thing I wanted to tell you that I just have to tell you in this class. I just have to tell you this, and that is that you have to know how to write functions here, because I mean this will save you so much time in R if you write a function. So I wanted to just kind of spend some time talking about functions in R. Now, what is a function? A function in computer science, and if you are a computer science major, then you know all of this. I don't mean to insult you. But a function is kind of like a pizza delivery person. So for instance, it's Friday night, I'm hungry, I'm thinking about having something to eat, I don't really know what to do. And so I call up my local pizza delivery group, and they say, hello, can I help you? And I say, yes, I'd like to have a pizza, please. And they say, great, what kind of pizza would you like to have? And I'll say, I'll have a big vegetarian pizza with everything on it. And they'll say, oh, that's great. So then they'll say, okay, we'll drop this off in half an hour. It's a delivery, home delivery. That is a function. I call them up, I give them some parameters about what I want the pizza to have on it, and what I want to order, first of all, what size. And then they return to me a pizza at my house. And so it's like I don't have to worry about cooking it. I don't have to worry about making the dough. I don't have to worry about slicing the vegetables, putting the tomato down. I don't worry about anything. I just give them the call and I give them the parameters, which is pizza size, the kind of pizza, and my credit card number, which is basically three parameters. And then the people at the other end take those parameters, they use them, and then I have no idea, for instance, what they do. But then before I know it, 20 minutes later, I have a pizza showing up. And so that is kind of like a function where I'm just giving a call. I'm calling out to some group, and I give them some parameters, and then they do something for me, and then I get something back. That is exactly what these pieces are here. This is your function definition in R, where, for instance, you have to give it a name here. In this case, I might call this the pizza place or the pizzeria, and then I have to tell R what I'm doing here. It's not just a string here. It's not an integer, but this is actually a function that I'm defining. And so this is the function here. This is us telling R that it's a function. Over here in the green, I have these are my arguments where I'll say, for instance, this is the pizza size, this is the kind of pizza, and this is my credit card number. And then over here, these are the internal workings of them making the pizza and putting things together and delivering the pizza. And this is the pizza at my door, the value that's returned. In code, what this is doing, I'm saying here's an argument 1, argument 2, argument 3. These are actually variables that hold information in the computer. And these variables then are plugged in to equations and formulas and code that's inside this function. And then after the function runs, it will return to me the last line here, whatever this is that I get on this last line, is what comes back to me. So that's kind of a strange way of talking about functions here, but I think that if we just go ahead and run a function, I think that perhaps you'll get. So this is a if you've done trigonometry recently, you probably remember the sine and cosine functions. Come with me to my RStudio, and I will show you what I can do with that. Get this out of the way. Oops. Last time, I think. So let me just go ahead and remove that. Open up a new file in our script, and what I can do is I'm going to define define a function. And so this is what my function is going to look like here, where I'm going to put some. It's going to be this. Now, remember that I know it doesn't make it easy to copy and paste things. I understand that, but remember that you can always add comments into your work, just like I'm doing right now with dates. So this is not great. Bigger or something. I'm trying to make this bigger. I'm doing everything that I've been told I could do. It doesn't. Ordinary. Let me see if I can get this. I'm going to try and make my text a bit bigger. Why this isn't looking like good. And sometimes it does. Okay. There we go. Oops. A bit too big. Okay, so maybe that's better. I don't know. Hopefully you can read that with a bit more clarity. Now, so this is my thing here. So now, it's a strange. This is different from Python when you're putting together a function. But what this is going to do is it's going to just return to me a value of sine. So like a sine wave, for instance, where I have like sine of, I'll put 5 here. 5 is my parameter, and I go ahead and run this thing. Actually, first of all, I have to run the function. Gracious. There we go. And you'll see that in your global environment, you'll have a function that just shows up. And then when I run my function, I get this value here. This is going to be value in radians. It's not degrees. So if you're using your calculator on your phone or somewhere else, make sure that you have your radians option turned on. Let me think. Okay, so going back to the slides, come with me back to the slides if I can find how to get back to my slides. Oh my gosh, it's like I can't get back to my slides. You do have some pretty cool stuff you can do with functions, though. Functions are actually quite good because they allow you to do a whole bunch of work repeatedly without having to write new code. So imagine, for instance, like if I wanted to do, I'll just do another function here. But imagine, for instance, that if I have a function, or if I have a need to calculate the square or the sum of squares, like many, many, many times, and I don't have to write the code repeatedly over and over and over and over again. Do that. Instead, what I could do is I would just make a function that would do that for me, and it's kind of like you're kind of automating something here. And so my function would look like this. I mean, you can actually put everything on one line if you want. I mean, you can do that, or if it's easier for you to work with, more complicated functions might be on 3 lines like this. It should all work. Big deal. All the same old thing here. Now, what I'm going to do is I'll type in. I can actually run the function here. I'll type in sum of squares, and I can have, like, for instance, what is 3, which is going to go into my x value, and I'll put the other value, which will be my y value. I'll put that as 4. Good old Pythagorean theorem here. And so when I run this thing here, it's going to say that x is equal to 3. So 3 squared is 9. Y is equal to 4. So 4 squared is 16. So 9 plus 16 is going to be equal to 25. And it's that way that that's how we got this value here. So I do hope that this is helpful. Again, if you are a computer science person, if you had experience working with functions before, then I don't mean to insult your intelligence. But I think that when you're working with functions, if you haven't seen them before, they can be rather confusing. But here's another function I wanted to show you, which is actually a little bit more interesting than some of the other ones here. This, I think, is actually going to be, this is going to be producing a very kind of small base plot for it. In fact, you can go back and you can read about, you can see kind of like how we can make this work. But really, what we're doing is we're going to be creating, I'll just say that my x's are going to be equal. In fact, this is my slides, but I'm going to of it. My x's are going to be a variable from, let's say, 2 to 10. If I run x, I get this an array. And I'm going to do the same thing here with my y. I'll just say that y is going to be also an array of everything from, say, again, I have to use this c because it's an array, 2 until 10. Oops. And if I go ahead and run, I'll show you y, again, I get the same thing. So really, it's a copy of each other. Now, I'm going to go ahead and just type in red plot, which is, oops, I need to run this. There we go. Red plot, I'll have x and y. So these are going to be my variables. If I go ahead and run this, can't really show you again. I guess it's in the corner here. It's this. So it makes a very, very basic plot, which is actually kind of a cool thing here. But you can actually do some quite exciting stuff with your. Let me just go ahead and copy this up here. You can do some pretty exciting stuff. Let me just show you another plot that you can make, which is where you can actually do change this around a little bit so that we can see some cool things. I'm going to modify my red plot just a little bit here. I have this. Let's call this red plot 2. Oops, what happened here? These faces. I'm going to make a plot, and one thing that we haven't talked about though is this other command here called type is equal to L. This actually says, give me a line. Show me a line. Show me how the lines are put together. So we have our old plot here. I'm going to put this red plot. Oops, I'll just copy this out. And I'll call this red plot 2. And when I do this, I get this line. So now what I can do, and this isn't in the slides, I'm going to kind of freelance here, but we have this function here called get Sine here. And so what I'm going to do is I'm going to connect my red plot with my get Sine. So let's see how I can do this. How about I'll just go ahead and say red plot 2, and I'm going to say x. But now I need my y, and y is going to be a value which I'm going to send to this function. And I want this function then to do something with each y value. Remember, each y value as it stands is just 1 through 10, or sorry, 2 through 10. I want it to return to me the Sine value. And then that value will come back, and then I'll get this something I can plot here. So I have this get Sine, and I'm going to put y in there. And there we go. I get a wave. I get a wave here. And so this is what they call a nested function, where you have a function right here, which is then using the input from another function. And so you have this two function system here which are working together. Um, I think that actually these functions are quite important here. You might spend some real time kind of if you're writing some code here where you have a lot of repetition and a lot of things are happening where for instance you're continually calling back to some function to do some type of analysis for you, then I think you cannot go wrong to do some to write uh, write a function to help you with your work. So that should help you. Let me just go ahead and save this. I'm saving my work now. I call it Focus 22 um, October 2020. This is so that I have this code written down so that I can get it if I need it. Okay, so come with me back to the slides. Let's go back to where we were. Find my way back there. That would be right now. Okay, here we go. So you have some information in your slides about how you can do some cool things. Here's a color plot. I think we worked on this in some ways. You can kind of you can play with some of the code here. But remember though, the actual work that's being done to plot this thing is this piece of code right here. This piece of code receives its inputs from the parameters in the function which are passed to it, like this. So here's the array of 2 to 10 being passed in for x. Here's another array of 2 to 10 which is being passed in y. And then over here I have this piece of this string here, which is blue, and this string is being passed in here. So that means color now is equal to blue. And so that's actually quite exciting to think now that you can kind of create a universal plot command. You can even use a universal ggplot command. And rather than having to rewrite that code each time you're working with something, you just throw in the x and y coordinates. Now you've got it. And so you can create many plots, all standardized. They're all the same. You may, for instance, even have other code inside here to add a label and to do some other things. And every time you want to plot something, you just call up this function in your code, and it will do the plotting for you. So you don't have to actually remember your ggplot code each time, which is exactly what I do. This is another plot that another function that I've created, which is actually kind of interesting. What this thing does is it takes in a number, and I'll just show you. This is actually working with strings, which actually is um, okay. I'm going to go ahead and drop a line here, and the next thing is this. I'm going to make this look a bit. I can see what's going on. Let me see. So I have this over here. I'm working with is in I'm missing some piece of information here. It's oh, you know what? My quote, and then I have down here another else, not enough. Okay, so what does this actually do then? So this is actually a very interesting function that I think actually does something useful. What it does is that you pass it a number, which is called the innum. I could have used any value I wanted to, any variable name that I wanted. But I just call this innum, as in incoming number. And then when you type in, like, for instance, give me at least 5 here, if I type in like 4.0, I run this, it'll say not enough. And so that means that it's doing a test. It's a conditional test. And your test is actually happening here where it's saying there, it says that if the number is greater than 5, if that is true, then print this statement here. However, if this is not true, then it could only be that this is false, and so therefore resort to this. And so, for instance, when I type in, give me a number of at least 4, or at least 5 here, and I type in my parameter is 4, 4 is not going to pass this test here, and so in other words, I get this line here printed out. So you can run this, and I'll just show you something else. You might say, how about 4.999999999? What does that thing do? It's still not enough because it still fails this test here. So if I go ahead and do another test where I have, okay, give me 5.0. 5.0, that is at least 5 because 5, incoming number here, does pass this test, and so therefore I get. So that is very cool. So now you can create all kinds of nifty functions, which I think you might find will help you with your own work. Um, okay, so I'm going to go back here. Come with me to the slides. Welcome back, and let's get on with it. So with that in mind, we're going to talk about statistics. And the reason why actually I was talking about these functions, because many times when you're working with some types of analyses, you might actually create your statistical analysis in a function. That means you may have your function running some kind of analysis of your data sets because chances are you're going to have many data sets which you'll be analyzing. And so you might just make a function that just analyzes all those data sets with the same types of tests. Like for instance, the mean, the mode, and some of those other ones that we'll talk about today. You may have those all in a function here. Anyway, sorry. So let's talk about the medians here. So the median of data is like the middle number in your data. It's the middle number. These equations that we're looking at right now, 10 plus, or sorry, x plus or n plus 1 over 2, these are not the numbers themselves, but these are rather the locations of those numbers. So you're taking you're finding the middle value of these numbers. So the best way of explaining this is just to show you a value or a system of numbers. Here we have numbers that range from 63 to 81. They've been sorted here, so they're in numerical order. And the median is the question saying what number, not the average, but what number is found in the very, very center of this data set. In other words, what is like the very center number? And so you find that number by saying, okay, well, if the number of, or the, if the, I say the word number all the time here, but if the number of numbers, if the number of values is odd, then what you can do is you can just, you can find the middle number using an equation n plus 1 over 2. So n is the number of values. In this case, what do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 values ranging from 63 to 81. So 9 plus 1 is 10 over 2 is 5. And so this is saying the median is the fifth number along in the lists. So 63 is 1, 64 is 2, 4 is 3, 60 or 70 is the fourth one, and then 72 is the fifth number. And so that is how you find your median number. Now, if you had, for instance, if we had some numbers, if you had an even number of numbers, then what you need to do is you need to find what really works out to be the average of the two middle numbers here. So if you have an even number, if you on the right hand side here, if you have an even number of values, then you have this other equation you have to work with, which is n over 2, and that will tell you how to find that value. Okay, now we're talking about in this thing here, we have Q1 and Q2. What does that actually indicate here? These are what they call the quantiles. And so you have this quantile data here, or the quarters of data. I've seen it as quantiles and quartiles. I'm not really sure whether that's that's right here, but quantiles is here. And so what these are is basically you're telling people where the data is falling in a kind of a in a plot that looks like this, in a kind of a bell graph plot like this. And so you have Q1, which is like your first 25%. Q2 is your second 25%. Q3 your third 25%, and then you have the rest of it, which is your remaining 25%. And so you're really taking a kind of a plot like this, and you're breaking it up into fourths. And the idea is that if I say that most of my data fell into Q1, the Q1 quantile, then that should give you an idea that the data fell on the left of the middle line here, Q2, which is the median. Like in other words, it's above, or it's no, no, it's just before the average line here. And so where we're going with this is that we're trying to find language to describe these plots without having to show people the plots. So you can see that, for instance, if here's some data. You can see that QNums, as I called it, I wasn't really call it this data that we have here. When I ran this through this command here called summary, which is actually quite cool, I'll show you this in a moment here. I can see, for instance, the first quantile and the third quantile, and so I can see kind of those numbers, or I can see what the number that fell in the first quantile and the third quantile here. So for instance, I can see that 725, this, if you can see this, this was my first quantile. And then 1415, it's right here. This is going to be my third quantile. So I know that my average mean must be in here somewhere because this is my kind of like my bound, I guess you can call it, my left bound or my first quantile, and this is going to be my right bound or my right quantile, my third quantile. And so I know that inside here, most of my data is actually fitting. And so this, I know this doesn't really look that, not that easy to actually swallow right now, but it will get easier. And that is that when you start thinking about sharing data with people, like locally, using language like this, you won't have to necessarily show them the plot. Of course, if you show them the plot, it will help to kind of drive home some of the points you're trying to make. And that's a good thing. But you'll find, for instance, that maybe if I just say, oh, I'm running my data right now, and I found that my summary, according to my summary, my first quantile is at 7.25. So this plot, by the way, has nothing to do. But I'm saying that my first quantile is 7.25. That means that my first quantile is here. That means that most of my data is going to be between these points here. That's all this means. It's saying, where did the data find itself? We plotted this. If I did make a plot, if I did make a plot of some form, where did the data hide itself? And we can type in this command here called summary, followed by an array of numbers. And summary will tell us what the mean, the median, the quantiles are. It's actually a really convenient. It's a really convenient type of command to have. Get it on one line. So I have the minimum actually in here, which is actually quite nice. That's the minimum. I have my maximum number, which is nice over here. I can tell, like, you know, if these were donations, for instance, for a political party, I can see that what was the minimum donation that anyone gave, and that was $3. And I say, what's the maximum donation that anyone gave, and that was $20, if that were the data. So that's how you could use that information here. But I could say that in general, most people gave money between here, this is the value itself, not the position, but the value itself, 725. So I'd say basically the values fell between this number and number over here, 1450 over here. So this is where most of the numbers fell. Now that's important because it shows you something about how the numbers are scattered. So for instance, if you said that if you had like these numbers, you found that most of those numbers were like, you know, 19, 20, 20, 20, 19, 19, 20. It's like most of them were up, big numbers. Then these quantiles would shift around a little bit, and so you'd have an idea about where some of the data would be found. Okay, but I mean, you'd see the mean and the median would change, and so that would give you some ideas about what the numbers were. I'm getting ahead of myself here. I don't want to go too far, but there's other things to discuss about these things. But if you just remember though that here's like your kind of your quantile system, your cheat notes. I guess you can look at it, kind of remember what's what in each quantile. But here's your first quantile, here's your third quantile, and your second one is going to be right here. But remember, the second quantile is really the same as the median, which we discussed here. That's your second quantile. So these things are all very related. But remember though, they're not designed to confuse. They're designed to give us language that we can use to actually vocally describe results that we would have otherwise had to show people by thought. What next do we have here? Okay, so let's go ahead and just try some, go back to some data and just get some results in this summary command. I mean, it does actually produce some pretty sophisticated statistics in seemingly no time at all. Now, of course, when I paste this, I'm going to get everything all mixed up, jumbled together. So let's see here, summary, your data. So again, we have this data that I'm using called air passengers. I'm not exactly sure what this is. I'm thinking this is like the number of people who are flying on a particular day, or maybe a gate in an airport. I have to find it. For now, though, it's good data. So I can run this summary on this and say, okay, well, give me the summary data for this air passengers column. And I can see, for instance, that the first quantile is 180. Here's the median. Here's the mean. And my third quantile is 360. And so if I look at the data itself, I get an idea kind of that it seems that most of the data is scattered between 180 and 360. It's like it's between these two numbers here. And that kind of makes sense if I'm looking at, oh, sorry, it makes sense if I'm looking at my data here. It doesn't, it didn't start at one, it didn't start at bigger, these are three big or three digit numbers. And so the whole point of this information here is that you do not necessarily, I mean, you should always see the data, but when you're describing the data to people, having a conversation about this data, then um, or writing about it, you do not necessarily need to show a plot to show them to show what the data is looking like. Um, this is a surprisingly powerful tool to have. That means you can just broadcast this information, you can write it down, you can say it, but then people should, in their mind's eye, have an idea about what the plot will look like. Of course, you can always plot the data like. Um, so let's move on to the next thing here. I'm going to go back to the, so here, also in summary, we have the min, the max, the mean, and the median. We've discussed the median here. I gave you the mathematical equations to do this, but I still think that it takes a long time to do these calculations. And so when you have something like summary, this provides this information for you, just like that, it makes everything so much easier. And also the mean, which is the average, right here. Mean is the average. The min, the max, the mean, and the median. 4 M's to remember here. I think I'm move on. The next thing I'm going to talk about though is correlation. This goes back to that plot that I was talking about earlier, where, in fact, I can show you again on the plot where we were working with. Oops, where is it? Here. We're talking about a correlation between these. This is suggesting that there's a correlation between uninsured Americans and unemployment rate. And so we're talking about a correlation, and the correlation is saying that when one thing is going up, the other thing is going up. That means that in this particular plot right here, hours spent studying. This is saying that the more hours I spend studying, the better my grades are. In theory, of course, it's not a perfect system. These points, as you can see, are kind of moving around, like underneath my direction here. The points do kind of shift around. It's not a perfectly linear thing. But when you plot these correlations, though, R will do its very best to create a kind of a straight line or a line so that you can look at the line and get a notion of what the points are doing. But this is saying that the more hours you spend studying, the better your grades are. That's a positive relation. This is a negative relation or a negative correlation, where, for instance, you have, let's see, we have time away from studying and interest level in classes. This is actually true. That if you're taking a class, like a history class or something, and you never read the book, you never go to class, you never care about anything, you kind of lose contact with that class. You suffer to actually lose interest, like you lose a lot of interest in that class, and so you may never go back to that class. It's like if you're not active in class, then you just lose interest in that. And so that's what a negative correlation would be. Time spent away from studying, and then you lose interest. And so as one thing goes up, as I spend more, as I spend more and more time away from my studies, then my interest level in classes goes down. And so that's what they call a negative correlation. One thing goes up, and the other thing goes down in function. Then you have, like, then for instance, correlations where nothing happens. Let's say the more I talk about Star Wars, the less the more my friends care. That's this correlation here. They don't care. I can talk about Star Wars all I like, and they don't care at all. It makes no difference to them whatsoever. They've moved on. They're talking about other things, and so it doesn't matter. And so there's no correlation. That means that you can put the plots on this in a plot here. You can actually make a scatter plot. But you'll see that nothing actually. There's no lines that can be generated. Nothing has changed. Here we have time talking about Sherlock Holmes, level of programming skill in R. Two things that have really nothing to do with each other. And so it doesn't matter how much time I spend talking about Sherlock Holmes and my level of programming skill in R, they're just not connected. There's no pattern. So here you have kind of like that was when you look at the plots, but when you're actually talking about, like, if you're discussing this with somebody, imagine you're talking to somebody over the phone and you have to give them a number to just describe some correlation. Well, you can do that too. Again, you can use language to describe a correlation. And so correlations extend between 1 to -1, 1, 0, and -1. 1 being a positive correlation, a perfect positive correlation. So usually you don't find perfect positive correlations, unless of course you're correlating a number or a group of numbers with itself. Um, so that's 1. Then you'd have, like, for instance, a correlation of 0 indicates that there's nothing going on. There's no connection between the two. That's basically this. And then if you have a negative correlation, -1, you have something that looks like this. Again, it is very rare to find a perfect correlation of 1 and -1 and 0. Usually those numbers are floating point numbers where they're actually very, very small, but still you have to think in terms of, like, well, it's kind of close to 1, it's kind of close to -1, or it's kind of close to 0. And that should give you an idea in your mind's eye about what the data would look like if you were to actually plot the correlation. That would be either this, or it would look like this, or it would look like that. No correlation ever. These are some other correlations that you can look at here, and look at the R value that they use. In fact, like this, right underneath where I am right now, the R value is on the left upper plot there is 0.34. Never mind about the t for a second, or the p value for a second here. Just think about the R value. What this is saying is that you have a value which is actually quite close to 0. It's on the right-hand side of 0, but still close to 0, which is suggesting that there's a very loose correlation that exists between advertising expenditure and sales. Now, in this next, going on the upper right plot here, you'll see that my R value, I don't like these values using the word, or the character R, by the way. It should just be called correlation equals, no mistake, because R could mean different things in different people. But in this case, R means correlation. So here the correlation is 0.96, which is probably as good as it gets. I mean, you can't really expect to get a correlation of 1, unless of course you're correlating some data set with itself. So here, 0.96, that's, I would say, very, very close to 1. It's very, very close to 1 here. So I'd say that actually if I were on the phone to somebody and they said, hey, tell me, what was the correlation between advertising expenditure and sales? I'll say, I got you, man. It's R equals 0.96. And they'll think, oh, wow, that's an amazing correlation, positive correlation. Things going together, right? But then I don't have to show them I shouldn't have to show them the plot. Of course, they should see it anyway. But by my telling them that the correlation has a value of 0.96, then they should just know in their mind's eye what it should look like if they were to see the plot. Next, on the lower left, we have 0.76. Oh, sorry, from 0.72. This is another kind of a loose correlation. It's not as in step as the correlation 0.96 that we saw. 0.72 is still not bad, but it could be better. And then here we have on the lower right, we have R is equal to 0 or negative 0.99, which is actually a very negative correlation. Again, it's you can't expect to find correlation -1 here, but this is very close to -1. So therefore, we're going to say that it's a very negative correlation. So sales and advertising expenditure negatively. These are some other plots you can look at where you have different types of algorithms that you can use to actually show correlations. Some of them actually do create some quite exciting looking pieces of art here, but these are plots that you put together where when you actually make a scatter plot, you put your points on the screen or on the canvas, and you can see certain types of designs. There are actually metrics that you can use to determine whether those plots are actually, or whether your points are actually showing a correlation, or whether they're just randomly scattered. So, for instance, if you look at the middle here, like if you look straight underneath where I am right now with the Pearson R is equal to 0.0 in the middle. It's basically a scatter of a cloud of points. Nothing crazy is going on there. In a linear type of plot, it will just be a straight line. And in these plots here, where you have actually kind of cool shapes that come out, your plot would look like this. This kind of like this, kind of a widened horseshoe, I guess you call it. But what I'm trying to say though is that these plots, these designs that we see here, are an algorithm's way of kind of showing you what the kind kind of like how the points are correlated. So you have to kind of figure out what the x's and the y's are in this case here to kind of understand what how they're correlated. But this is really where points are falling in your canvas. They all look kind of. Right. So anyway, you can look at these other things here, and you can get an idea. One more thing that I'll say though, that if you look at the upper left, Pearson, that's the algorithm that they use actually to calculate these correlations. The number itself, r is equal to 1.0. That number r, 1.0, it has to be calculated by some algorithm, and that algorithm was put together by a mathematician called Pearson. That's how they actually calculate values of r. There's other ways of doing it, but this is, I think that Pearson is the standard in R statistics, so you always get that value, which works fine. Right, let's move on here. Here are some ways that we can actually calculate some correlations in R statistic, which is actually a real benefit here, because then if we wanted to calculate these values R that we see here, how could we do this in our data set? Well, come with me to the our statistic, our studio, and try it out here. I'm going to put this here. I'm going to go ahead and paste that. Of course, when I paste this stuff, it never comes out looking fine. Assuming here, let me just. Oops. There we go. So we have correlations here. So the first thing you should try though is this core. If I go ahead and put a question mark in front of core, you have this. I hope you can see this very well. But you really have an extensive online help. I mean, a really terrific online help. It doesn't come with all the graphics you might expect for other types of online help. But actually, though, it does come with code. And that's really what I think the code that you see in your slides is the same stuff that's coming out of here. So you can actually try out some of these code. So I'm going to go ahead and just I'll just create a correlation between, remember this value here, 1.0, or sorry 1 to 10. This is counting numbers 1 to 10. Here's counting numbers 2 to 11. This command that I'm running right now is saying how are these numbers actually growing? Like for instance, if I look at the plot of 1 to 10 and 2 to 11, what do I actually see happening here? C, move this, and when I run that, you get this. And so really, you can see this plot shows that as the x values are getting bigger, so are the y values. And so the correlation in this case right here is a 1, which means that as one thing is getting bigger, so is the other. You can think of correlations in terms of just that, like as one group of numbers is progressing, how does the other group of numbers progress in relation? Here's another one you can look at here, where I'm now looking at the correlation of 1 to 10 here, and then I'm looking at -2 to -11. I run this, you'll find you get a -1. And my plot, I'll just give you a quick heads up if you want to see what that looks like, would be this, where everything's going down. Going down, down. So that is your negative correlation. And then, for instance, let's see, what can I do here? Do I have any other cool code I can show you? Well, there's other cool code in here. There is something that's actually kind of interesting. If I go ahead and actually go back and copy that. If I, you can work with matrices here. Not that matrices are, you don't spend a whole bunch of time working with matrices now, but actually you can do correlation matrices to kind of get an idea about how certain columns of the matrix actually connect with other columns. And of course, I need to go through and put everything into some kind of an order here. So we have that, this, and this. Okay, so we have this core Longley here. This is some data that actually exists in our data set, in our library, and it's a GNP. This is economics information here, unemployed armed forces. You're basically having some numbers. The GNP, deflator, GNP, unemployed armed forces, population year employed. These are just numbers. Don't worry about what they mean for now. They're just numbers. You can find out if you want to know what they mean. You can type in Longley with a question mark, I think. So I can do that now. There we go. So I can find its long leads economic regression data. So now, suppose I want to see, like, for instance, using this data here, how does, for instance, this deflator number correlate to something else, like a year or something? How can I correlate these things? Well, so then getting back to our code, you have this some code here where you can type this simnum, I think it is. That's your correlation network. And so really what it's doing is it's taking each number here and correlating it for, sorry, it's taking each of these values here, the x-axis, and correlating them with the values on the y-axis here. So this is all data that actually is built in somewhere. It's more than just this. But now, when you run this matrix here, you can actually do a lot of correlations awfully quickly here. You're doing kind of an all against all correlation. Here you have to kind of, one thing that's kind of hard to reckon with though is that you have to kind of understand what these different characters mean. So for instance, here, if it's a zero correlation, you get a blank. If it's a correlation of 0.3, you get a period. If it's a correlation of 0.08, you get a comma. You get an idea. These are getting better. These at 0.08 is getting closer and closer to a higher correlation. If it's a plus that you see up here, that means you have a correlation of 0.9, which I don't see anything here. If you have a star, it's getting up there. You have a 0.95. And then if it's like a perfect correlation, you have a B, which is like right here. And I think that they actually put ones right here to show you that it's the GNP going against GNP. So it's like some value is going against itself. That's so you don't start looking at your data and seeing correlations which really don't exist. Of course, unemployed and unemployed, they do exist. These are abbreviated, by the way. A over here with armed forces. Of course, A and armed forces would be a perfect correlation, because it's the same data. But remember, what you're doing though is you're looking to see how does armed forces actually correlate to the GNP, which is this point. So that gives you a correlation point. And so this is a kind of a faster way of doing correlations, like multiple correlations, very, very quickly. I'll leave the other code here for later. We have, let's see, how much more time do we have here? We don't have. I think I'll just do the standard deviation, and then we'll call it a day. Be done with it. The next thing we're going to talk about is what they call the variance. And the variance is like the, if you were to find out like the mean of a whole bunch of points here, what is like the average distance between the expected places where the points would be found, the mean, and the points themselves? And so, for instance, here you can get this, you see this data, and in this data, I've calculated kind of like the mean of where those points are. You're looking at these points, and you calculate where the mean is. I'll talk about how to do that later on. It's actually code. But what I want to do though is I want to find out what is the average list or distance of my arrows. My little arrows here that point from, go from the mean arrow all the way to the little blue points. What is the average distance of those arrows? In other words, how far away is my collection of points from where they should ideally be if they were so-called expected? So that's what they call your variance. What is the average? What's that average distance here? Oops, I was looking at here. Sorry guys, I need to keep you away from that slide here. But this is what I'm talking about here. So my arrows are here. I'm just like measuring the average length of these black arrows that are in this thing here. So now if I go back to my R package here, let's go ahead and paste this in there. Oops, you know what? I need to edit that. So I have my data, which is called my data. And then I have the command that I'm typing to actually get the variance is called var. And I can see that this value here is 9.4. And so that's 9.4 is actually the average length of arrows the average length of my arrows between where the points ideally should have fallen and where they actually ended up falling. And then I have, for instance, my standard deviation, which is the square root of that number. So I can just take the square root for my data. In fact, I'll just show you what that looks like. Come back to the R statistical. I think I'm kind of running out of time here. Maybe I'll just finish it here and we'll talk about standard deviation when next we come together. But here we go. That's my standard deviation. Um, yeah, I think I'll stop here. I think that we'll come back and we'll pick up with standard deviation by next week. Next we meet on Tuesday. There is since we have a 2-week lab, by the way, there's no lab meeting tomorrow, just because you're still working on your lab. But if you have questions, you can ask. I don't want to make you think that you're not allowed to ask questions. Of course, you're allowed to ask questions. And so let me know. I'm available on Slack, but I'm just not going to be logging into the lab meeting. There's no meeting tomorrow because you're still working. Okay. Are there any questions anyone may have? No question? Okay. Yeah. So the quartiles. So we're looking at you're trying to figure out like where are the numbers going to like where are these values actually showing up in terms of a plot like this. So if I were to plot these values here and make a kind of a bell curve type plot like this, how could I break this thing up so that I can see where 25% and 25% and 25%, where do I find out, how do I break up this data to find out where the 50% of my data is? The 50% of my data is this section here between Q1 and Q3. That's where half of my data is found. Everything else found before the Q1 and found after Q3 would be characterized as outliers. It's falling away from the. So this is like a way of saying where did half of the data fall, and it's right here. And so you can look at these numbers here and kind of get an idea about where half of the information. Anyway, I didn't mean to keep everybody here for so long. If you have questions, you can use the Slack channel, whatever it is you'd like to use, and or send me an email or office hours, and we'll go from there. Everybody stay well. I'll see you all very, very soon. Take care.